In statistical sampling, the parameter estimation, one of the first steps, is to determine the necessary sample size. There are basically three factors that determine the sample size requirement, none of which has any direct relationship to the size of the population when the population size is larger or is infinite. In other words, a population size has rarely anything to do with determining the minimum sample sizes. The factors that do determine the required sample size for confidence interval estimation are the desired level of confidence, the maximum allowable error, also known as the margin of error, and the variation in the population being studied. In a later slide, you will observe that in the formula for computing a required sample size, a smaller margin of error requires a large sample size. Secondly, a higher confidence level estimate and populations with more variability will also require larger samples to maintain a certain level of margin of error. Conversely, estimates with lower confidence intervals, populations with smaller variability, and larger margins of error will require smaller sample sizes. As discussed in the previous slide, in determining the minimum sample size for estimating an unknown population parameter, one of the required pieces of information is a measure of the variability of the population. In many instances, however, the population variation is not known. In this case, we will need to use an initial estimate for the population standard deviation. Here are three suggestions for finding that estimate. One, you can conduct a pilot study. This is the most common method. Suppose we want to estimate the number of hours per week worked by students enrolled in the College of Business at the University of Texas. To test the validity of our questionnaire, we use it on a small sample of students. From this small sample, we compute the standard deviation of the number of hours worked and use this value as the population standard deviation. Two, we use a comparable study. Use this approach when there is an estimate of the standard deviation from another study. And three, we can use a range-based approach. To use this approach, we need to know or have an estimate of the largest and smallest values in the population. The formula for computing the sample size needed for estimating the population mean is given as the square of the product of z and sigma divided by e. In this formula, the z represents the level of confidence that one wants to associate with the estimate. Sigma represents the population standard deviation, which is a measure of the population's variability, and e is the maximum allowable error for the estimate. We note that in this formula, when we want a more precise estimate, that is an interval estimate with a small margin of error, a larger sample size will be required. Similarly, a higher confidence level, assuming the margin of error is the same, requires a larger sample. For populations that are fairly homogeneous, meaning the standard deviations are smaller, a small sample size will be sufficient to generate a given level of confidence while maintaining a certain level of margin of error in estimating the population mean. On the other hand, heterogeneous populations require a much larger sample. We demonstrate how to use the formula for computing the sample size requirement for estimating a population mean here. Consider a problem where a student in public administration wants to determine the mean amount of members of city councils in large cities earn per month as remuneration for being a council member. The error in estimating the mean is to be less than $100 with a 95% level of confidence. The student found a report by the Department of Labor that estimated the standard deviation to be $1,000. So what is the required sample size? We identify the given information in the problem. They have given us the maximum allowable error E of $100. The value of Z for a 95% level of confidence is 1.96. And you may want to refer back to the Bottle Blowers of America example presented earlier to see how to obtain the Z value using the standard normal distribution table. The estimate of the standard deviation is 1,000. Substituting these numbers to the formula, we obtain a sample size of 385. To put it another way, the student will need to sample a minimum of 385 city council members in large cities in order to determine a 95% confidence estimate on the true mean monthly earnings of large city council members, so that the error of the estimate will be within $100 of the true value. The formula to determine the sample size of estimating a population proportion, similar to the formula to determine the sample size of estimating a population mean, is also comprised of three components, namely the variance of the population, the confidence level, and the maximum allowable error. The confidence level expressed by the z-value and the margin of error E are established by the investigator. If an initial estimate of the proportion pi is available from a pilot study or some other source, it can be used in the formula. Otherwise, we use 0.5 for pi. When we use a pi of 0.5, we generate the largest possible sample size for a given margin of error and confidence level. However, if an initial estimate of pi is available, especially when it is smaller than or larger than 0.5, the resulting required sample size for a given confidence level and margin of error will be smaller. This will result in a lower cost as well as less time for sampling while achieving the same level of accuracy and confidence level in our estimate of the population proportion. We apply the formula for computing the sample size of estimating the population proportion in this example. The American Kennel Club wanted to estimate the proportion of children that have a dog as a pet. If the club wanted to estimate the estimate to be within 3 percentage points of the population proportion, how many children would they need to contact? Assume a 95% level of confidence and that the club initially estimated that 30% of the children have a dog as a pet. So we translate the 95% level of confidence into a z-score as 1.96. Then using the initial estimate by the club that 30% of the children have a dog as a pet, we substitute 0.3 into the pi in the formula. Thus, 1 minus pi is 0.7. Since the club wants the estimate to be within 3 percentage points of the population proportion, we substitute 0.03 for E, the error, into the equation. Solving for n, the sample size, we obtain the answer of 897. What this means is that the AKC will need to contact 897 children in order to estimate the true proportion of children that have a dog as a pet and still be within the 3 percentage points of the true proportion and be 95% confident of the estimate. So what do we do if an initial estimate of the proportion is not available? The example on this slide shows how to compute the minimum sample size for estimating the true proportion given a 90% confidence level is desired, and the estimate is to be within 10 percentage points or within 0.10 of the true proportion. Since an initial estimate of the population proportion is not given or is unavailable, then in this case we're going to use pi equals 0.5 in the formula. Using a pi of 0.5 in the formula assures the largest possible sample size for a population whose variation is unknown while maintaining the same confidence level and maximum allowable error. The z-value for a 90% confidence level is 1.645. We substitute these numbers into the equation, and computing for n, we obtain the sample size of 68.